The Crossland Hill Observatory was a big project for the club during the 1970s, and when finished housed one of the largest telescopes in the north of England at that time. Batley had a 15-inch and Sheffield an 18-inch. This is the story of how the observatory, along with its telescope, was built. The photos are all digital copies imaged from the original 35mm slides. Each of them has been treated to remove dust and scratches, and where possible colours have been restored and graininess removed by smoothing. This is a view of the current observatory taken from across the valley near Out Lane. Like many clubs, Habs talked over the idea of building a large telescope. At that time this meant an equatorial mounting requiring an observatory. The subject had often been discussed during the 1970s, but only became a serious consideration in 1974, when visits were made to neighbouring clubs who had already undertaken the building of an observatory. For some years Philip Pendred, that's myself, had run a telescope mirror making class in the Railway Street Club Room, where many members of HAPS and other clubs had made their telescope optics. After much discussion regarding the aperture, resolving power and possible costs for a glass blank, a 16-inch mirror made at the club was not considered an insurmountable problem. One of the main driving forces behind the project was the then club president Philip Heppenstall, who as a keen astronomer, engineer and designer had many contacts in the engineering field, and also the firm belief that the telescope and its observatory could become a reality. Our first priority then was to find a suitable site. It was during a ramble over Crossland Hill in mid-April 1975 that Philip Heppenstall and myself came across the remains of a wartime Royal Observer Corps Type Q observation post. It was situated at the edge of an old quarry, which at the time was being used as a tip for building rubbish. We later found a similar post on the ridge behind the ICI factory, just off Leeds Road. It was a substantial brick building with a thick concrete roof and had clear open views in all directions. This is the view looking south over the moors. There were few street lights in this direction to spoil the sky. In all, it was a site worth thinking about. Inside the building were the remains of the supporting pillar for the Observer Corps theodolite, and overhead an octagonal hole in the roof, through which their observations of incoming enemy aircraft had been made. The lady in this slide is the then club secretary, Mrs. Minor Beaumont. A 10-year lease on the building was quickly organised, and clearing out the accumulated debris was started. Preliminary plans were made and the roof aperture was shuttered up and concrete poured to make it a door-sized rectangle. I did this over a couple of weekends, most of this material coming from the tip just a few yards away. This included the shuttering, bricks, angle iron and even unused cement. Originally we thought that the roof would be adequately strong enough to support our envisaged mounting, but tests on a clear night with a smaller 8-inch instrument showed that there would be considerable vibration from people moving about on it. It was therefore decided that the mounting, although not yet designed, would have to be supported on a concrete pillar, passing through the roof, and so work started on cutting a suitable hole. As we had no power or water on site, this was done by hand with a hammer and chisel. It took several weekends to hack through the 6-inch thick reinforced concrete. As we needed to anchor the pillar securely into the ground, a square hole had also to be cut by hand through the similar 6-inch thick reinforced concrete floor, and a 1 metre square hole excavated down to the bedrock beneath. This is the view looking down through both apertures from roof level. Philip Heppenstall is standing in the excavated hole dug out for the base of the pillar. By July 1975 the initial plans had been worked out, at least on paper, and submitted to the Kirklees Planning Department, and fundraising was started in earnest. A 16-inch mirror disc had been ordered from Schatz Glass in Germany, and inquiries were made concerning a 15-foot fiberglass silo dome, which had to be obtained. In the interim the building was made vandal-proof, windows bricked up with material from the tip, and work was started on extending the roof to form a square. In August, Robert Beaumont and Philip Heppenstall arrived at my house in the town centre, with a door that Robert had made for the building, and we set to work covering this with a steel sheet, and edging it with angle iron from bed frames that I had salvaged from the tip. For some reason there seemed to be an unending supply of old bed frames to be found there. The following weekend I took the completed door up to the building on top of my old Beetle and screwed it into place, so making our observatory reasonably secure. The roof openings were covered with corrugated steel sheets fastened down from the inside, and from then on it was possible to stock materials inside the building. Throughout 1975, Philip Peppenstall had sent out letters soliciting help from many local firms, and we were rewarded with the delivery of bricks, at half price, from Elliott Bricks Limited of Lepton, who delivered them directly to the observatory door. Note the footings dug for the eventual short length of wall that would support the roof extension. A weekend was spent by myself and Robert sorting the bricks and stacking them ready for use within the building. We found that half price actually meant half broken or bent in half, but there were sufficient complete bricks available to do the job. Fine weather during September 1975 meant we could attack the roof construction by chipping away the edge at a suitable angle to support the new section. The roof, which was L-shaped, had to be made square in order to take the circular supporting wall and dome. Robert brought up his portable generator and a Kango drill to speed up the work. Unfortunately, the hardness of the concrete meant that the Kango was actually a can't go, as he proceeded to dance about all over the roof without actually cutting much at all. Philip Peppenstall and myself did most of the work by hand with a lump hammer and a chisel. By October 1975, after waiting several weeks for the local building inspector to visit the site and pass our short length of foundation as fit to use, the supporting wall was built up by Jack Beaumont, the secretary's husband. An RSJ and steel sheets, courtesy of William Arnold and Sons, were fitted into place to hold up the new roof section, and work started adding the concrete. A couple of weekends were spent in pouring and levelling the concrete, which had to be mixed by hand using water I had brought up to the site in 20-litre plastic containers, as there was no mains connection, no electricity and no mixer. With the extension complete, the roof was now essentially square and of sufficient strength to carry a circular brick wall supporting an eventual rotating dome. Some 6 months earlier, and after much discussion, it had been decided that a 16-inch mirror could be made, and in June 1975 an order was placed with a shot glass company in Germany for a 16-inch disc of Duran 50. This was 3.5 inches in thickness and weighed about 70 pounds. At a cost of £160, this almost depleted the club's bank account, and so, as well as working on the observatory, I had also to start on the mirror. This is the Examiner photo to publicise our acquisition. It's very unscientific. The first step was to grind out the irregularities in the moulded surface prior to starting work with a full-size tool disc, which was purchased separately for £60. Grinding, polishing and optical testing of the mirror was done at the Haps Club Room, where I would work on the disc most evenings, sometimes until well after midnight, 3 to 4 times a week for over 6 months. In this photo the mirror is being fine ground, its curvature having already been established and giving a focal length of 7 feet 6.5 inches. As previously mentioned, the mirror disc weighs 70 pounds. As the clubroom sink was too small to accommodate such a large disc, a special washing box was made by John Naylor, and was worth its weight in gold. Back at the observatory, with roof now square, work had started on the construction of the circular wall. Here Jack Beaumont lays the first bricks. In order to ensure a truly circular wall, Robert Beaumont had constructed a curved metal guide plate. It was supported on a vertical scaffold bar centered on the roof, and it kept the wall at the correct radius. The curved plate also slid around the exterior of the wall to retain some sort of verticality. In this photo, Robert and Tony Pike are checking the progress. On days and evenings when not down at the club room mirror grinding, I was also up at the observatory laying the bricks. The wall gradually gained height, and although not by any means perfect, was at least vertical and circular to a reasonable degree. In order to maximise the support strength for the proposed 15-foot dome, a second circular wall was built inside the first. Here I'm working next to the opening which would eventually become the access door to the observing floor. By August 1976 the double walls had reached their full height, and recesses had been left to take the ball rollers on which the dome would rotate. These had been supplied by M.H. Mear & Company. This photo shows the appearance of the observatory with its completed circular wall. On several occasions we were asked by neighbouring golfers visiting the 13th green if we were building a chimney. The year previously, in June 1975, our problem was to find or make a suitable dome. By pure chance I discovered from the Look North television programme that Hippo Mouldings of Horbury had some deformed fiberglass silo dome sections which they had to dispose of. I cycled over to Horbury the following Sunday and clandestinely did a bit of trespassing to find a field containing piles of different sized sections, some of which seemed to be of the required size. The following Monday, Philip Heppenstall and myself visited the firm, and after explaining our needs were pleasantly surprised to be offered 2 domes of the correct diameter, and furthermore they had free delivery. John Naylor kindly allowed the club to use his garden as our construction site, little realising that we would be regular visitors for the next 2 years. The first task was to see what we had been able to obtain, and Philip Heppenstall and myself assembled the sections by lightly bolting them together. We had sold one of the 2 domes to another club, but we retained enough sections of them for our own use. As we already knew from the manager at Hippo Mouldings, the sections did not make up a perfect hemisphere, and in any case they were known to be faulty. Nevertheless, it was a start. The dome required a vertical skirt, and for this we needed 2 support rings. With his engineering contacts, Philip Heppenstall approached Peabody Holmes of Huddersfield, where he worked. In March 1976 they offered to roll the 6 sections of 3-inch steel angle which they had donated. This was to a radius of 7 feet 6 inches and suitable for our dome. I spent a couple of weekends carefully levelling concrete-filled oil drums, and we bolted the top ring together. There were occasional visitors to survey the progress, but few offers of help, and the dome construction was left largely to Philip and myself. With a little persuasion, the dome was re-erected on the levelled upper steel ring, and work started on the shutter mechanism and the slot. Philip had constructed a cardboard model showing how the shutter would function. It was a novel concept, but something out of the ordinary was needed, as the dome was never going to be a proper hemisphere. In this photo we have cut out the slot and formed a shutter from spare dome sections. It was held in place temporarily by bolts of wood. It must be remembered that during this time we were also working on the observatory building, and I was working on the mirror and Philip was designing the telescope. It was becoming a rather full-time job. This is a view looking up into the apex of the dome, where the ball race on which the shutter turns is located. For those who visit the observatory today, the way it functions is easy to see, but during construction we were not so sure that our cardboard model and reality would behave in the same way, because the shutter, being fixed in place and not complete, could not yet be moved. With the preliminary measurements completed, we dismantled the shutter and had it transported from John Naylor's to my garage in the town centre, where Philip and myself spent a couple of weekends fiberglassing edges onto it, so that it would retain its curvature and eventually form a rainproof type of tray. As you can see, there was not a lot of room to work, but at least the acetone fumes could escape. With the shutter now more or less complete, it was taken back to John Naylor's, refitted into the dome, and lead counterweights added to the opening mechanism. Wires were then temporarily fixed into position. The mechanism for pulling down the shutter so that it would clear the upper part of the dome was, and I believe still is, a pair of lawnmower handles supplied by myself, and which proved to be ideal for the job. Later, once the length of the wires had been finalised, I cut slots so that the handles could be disengaged and lowered out of the way. Work continued on this part of the project throughout the winter months, even in the snow. Once we had found that the shutter would probably work, Philip and I dismantled the whole dome once again, and then rebuilt it a second time, including now the lower ring, which was levelled on the concrete drums. The 2 rings were now separated by 6 steel verticals, which were bolted into place to form a rigid structure, around which the vertical skirt was to be attached. In this photograph I am fixing the supports for the shutter opening mechanism. These had to be carefully positioned in the centre, as if they were not, the shutter would be incapable of rotating around the inside of the dome. To support the sheet aluminium skirt, numerous vertical timbers were cut to fit between the rings and screwed into place. These were all numbered, as no two were exactly alike. In the background you can see the completed shutter. By now, June 1977, the aluminium sheeting to clad the dome had arrived on site, i.e. John's gun. This was a donation from Hanson's Haulage Limited, being sheets from the sides of the company's vans and lorries. Each piece was measured, flattened where necessary, and the ends turned over to form a neat edge. On occasions the younger end of the club came visiting to see what progress we were making. Here we see Simon Smith, Paul Harper and Martin. When these visits happened they were put to useful work, things like stirring paint and picking up the dozens of rusting broken drill bits, or sorting out which nuts would screw onto which bolt. Once the sheets had been measured and cut to length, they were screwed into position around the dome to form the vertical skirt, hopefully with sufficient clearance for the observatory wall. Both Philip and myself worked in all weathers. Note the once pristine lawn now becoming just a little muddy. Protecting electric cable from the wet was also another problem. By the autumn of 1977 the skirt had been fixed into place, and we had started replacing the dome onto the upper ring, this time with the majority of the bolts to ensure it had been pulled into the correct shape, as we had now to refit the shutter and make it weatherproof. The reassembly of the dome was almost complete, although the upper ring had still to be cut where the shutter was to go, and holes here and there were still to fill. In this photo I am fitting the outer edges to the dome aperture. Each piece was cut to shape and then fiberglassed into position. Access on the inside was by a precarious ladder perched on an oil drum. Once the edges were in place the shutter could be tested. Philip's idea to use a modified car jack to push it up into position against the opening worked very well, and after some trimming of the edges it fitted perfectly, but leaving a larger area to be filled in with sheeting. The most difficult part of this assembly was making a section around the base of the shutter. This had now been fitted with a vertical extension carrying wheels. These were recessed to fit the top edge of the lower rail when the shutter was lowered. One of these can be seen just behind me. This slide shows the shutter in its lowered position. One of the wheels is visible, engaged in the lower rail, while Philip is in the process of adjusting the shutter's stop bearing, which will roll up a vertical plate fixed to the dome when the shutter is jacked up into its closed position. The side plates ensure that the shutter ends up correctly against the opening. Using the jack, the shutter could now be raised against the dome when being closed, and lowered onto the rail and rolled around within the dome when being opened. In the raised position it left a small slot to be filled. An aluminium sheet held in place by two removable bars completes the basic assembly. After almost 2 years of work, this is the completed dome, now just needing the finishing touches. For a third time the whole assembly was dismantled. All the parts were carefully numbered, cleaned, de-rusted and painted. All the wood was dispatched to be tannalized to prevent rot, and all the dome bolts were sent off to be plated, another task organised by Philip with his engineering contacts. Throughout the spring of 1976, as well as working on the dome and the observatory building, I had been grinding and smoothing the mirror. On April 6, 1976, it had been completely fine ground to the correct curvature of 15 feet and was now ready for polishing. The first step was to make a pitch polishing lap from the tool disc. This is done by sticking masking tape around the edge and so making a shallow dish to retain the molten pitch. The pitch is melted and poured slowly onto the pre-warmed tool disc. Facets which are required for even polishing were moulded into this pitched surface using a plastic sink mat. This was placed over the still soft surface of the pitch and the mirror placed on top, so forming a sort of sandwich. The sandwich was then pressed hard to force the pitch up through the mould and then left to cool with the weight holding them together. When the pitch had cooled and hardened sufficiently, the mirror was slid off and the mould carefully lifted away, leaving a series of moulded square facets. Polishing the finely ground surface was carried out using cerium oxide as the polishing agent and continued for another month. I worked 2 or 3 times a week, often for several hours at a time. Once the surface was completely polished, the mirror was gradually parabolized over the next few sessions using a different series of polishing strokes, and then serious testing of the optical face was started. The standard Foucault test was used to determine the state of the mirror, using a Coude screen to evaluate the curve and the zonal radii of curvature. In this photo, the mirror is on the test stand with the Coude screen in place. This is the Foucault tester. Basically, it's a pinhole and a movable knife edge controlled by a micrometer. It may look crude, but gave and still gives good results. It's used to measure the differences in the radii of curvature of different mirror zones, as is found in paraboloidal telescope mirrors. The following 3 photos, all quite long time exposures, show the mirror profile as seen in the test. They must not be confused with the actual surface shape. The first is with the knife edge set at the radius of curvature of the mirror centre. The mirror shows an apparent dome profile with a small flat central area. It's not the purpose of this talk to discuss the test in detail, but the appearance as seen here is normal for oblate surfaces like paraboloids. This is the classic donut profile, as seen when the knife edge has moved further back and cuts the reflected beam in the mid position. In fact, the knife edge is cutting at the radius of curvature of the 70% zone on the mirror. Again, this is a normal appearance. This third slide shows the sorts of shape one expects to see when an oblate surface like a paraboloid is tested, when the knife edge, having moved back even further, cuts the radius of curvature of the mirror's edge. Despite these apparently correct profiles, it is the measurements of the knife edge movement that have to be correct. In fact, the measurements made at the start of April 1976 showed some zonal errors, and the mirror was retouched to try and reduce these. Here I am working with the polishing lap face down. Retouching the parabola went on for nearly 2 weeks. With the polishing lap on top, pressure can be applied to one edge of the tool disc, and therefore the polishing action can be concentrated on a particular zone. This method has to be used with care though, as one has to work all around the optical face in complete turns before the next test can be made. Finally, halfway through May 1976, the tests showed that the mirror zones had readings pretty close to their theoretical values, and it was time to try a crude star test. On the 25th of May, I set up a simple wooden tube in my back garden and mounted the unilluminized mirror in it. A star test, in fact a null test, showed a slight undercorrected edge zone and a slightly raised central zone. Both areas are difficult to test with the standard Foucault tester in the clubroom. To deal with these zones, I made a small star-shaped polisher. A small polisher like this has to be used with care, as it is very easy to radically alter the mirror's shape. I made a few passes around the defective zones and did some more work with a full-size lap, and by the 27th of May 1976, tests showed that the wavefront error was about 1/10 of a wave, with a surface peak-to-valley error of about 1/22 of a wave. This was well within the agreed accuracy limit of 1/8 wave, and I considered that the mirror was finally finished. I made some Foucaultograms of various zones just for the record, each one being a time exposure of several tens of seconds. Not easy before the time of digital cameras. This is the mirror with the knife edge centered on the 31% radius zone. This image was taken with the knife edge pulled back a little to cut the 71% radius zone. Here we see the typical donut profile of an oblate mirror. The surface is smooth with no obvious scratches. Here the crests are situated at the 84% zone, the knife edge having been pulled back even further. And finally, the knife edge is positioned at the theoretical edge radius. The 16-inch mirror was now finished, apart from its aluminium reflective coating. It had taken me 6 months of work to grind out and polish the 3-inch thick 35 kg disc. It was finished on the 27th of May 1976. During this period, work had continued on the observatory, and Robert had made and fitted wooden shuttering, ready for pouring concrete for the telescope supporting pillar. Mike Henderson inspects the result. Note that there is no front to the shuttering at this time, as we had to gain access to the hole beneath the floor. Philip and myself had grouted lengths of steel reinforcing bar into the bedrock at the bottom of the hole to ensure that the column would not budge, and we awaited the delivery of sand, cement and gravel at the observatory site. Unfortunately, the firm delivering these items left them at the roadside about 150 yards from the observatory, and Kevin Dooley, myself, Paul Harper and Philip Heppenstall spent a hectic Friday moving tons of urgently required material up the path to the building. I think there were 6 tons of gravel and 4 tons of sand in all. This had to be done using a single wheelbarrow and a couple of buckets, ready for a start on the Saturday. No mean feat, and by the evening we were glad when the majority of it had been shifted. Saturday morning arrived, as did our petrol-driven cement mixer, and we were ready to start mixing concrete when, to our surprise, a team from the Bradford Astronomical Society led by Derek Devey turned up to give us a hand. Derek and several others from Bradford had made mirrors in my class and were keen to see what we were doing. It wasn't long before they found out. Most of the younger end of the club looked on as the rather battered cement mixer rumbled into life. One problem was the lack of piped water, and for some weeks previously I had transported gallons of the stuff up to the site and laboriously filled 3 or 4 oil drums rescued from the tip. Whilst the mixer chugged away outside, I prepared the hole ready to receive the buckets of cement. Derek and Philip kept the voracious beast fed outside. The weather that weekend was beautiful, thankfully. Inside, I poured the cement supplied to me into the hole and trampled it down, adding the reinforced mesh and vertical steel bars and wiring them together at intervals. At this point the front shuttering boards were not in place, and all that had to be done was to pass the buckets of cement in through the door and around the corner to me. It was a simple matter to empty these around my feet, making sure that the hole in the floor was carefully filled, but not allowing it to actually touch the underside of the floor. By midday the golfers were hard at it, and so were the junior members of the club, filling buckets of sand and gravel and bringing them to the mixer. Inside the observatory the column had reached floor level, and the vertical bars had to be linked by wire before the front boards were bolted and clamped into position to fully enclose the rising tide of concrete. This left me free to give a hand with the mixing, as once the front of the shuttering was bolted into place, the only way to fill it was by hoisting the full buckets of mix over the top of the circular wall. By the end of the Saturday the column was about half height. Sunday morning I prepared the joint between the 2 pourings by applying a layer of PVC glue. I didn't know if this would actually have any effect, but it had been recommended by the builder's merchant, so that's what we did. Dropping something down the hole like my helmet meant a bit of ingenuity to get it back. As already mentioned, the buckets of concrete had now to be either lifted in over the circular wall or hauled up by a rope through the stair hole. The latter route proved to be the most simplest. In this photo you can see that the shuttering boards prevent the column from touching the roof. In fact, the roof will become the observatory floor. Derek Devey came over again for the Sunday and took charge of the mixer. Here the last few buckets of concrete are being mixed. The mounting block for the telescope was to be cast last, and so reinforcing bars were left protruding from the top of the concrete. It was quite a relief after 2 days of hectic work to finish off the top of the column, not forgetting a fraught Friday moving the material to where it could be used. The end of a very busy weekend. All we had to do now was wait to see whether or not the column would come up to our expectations. A month later the shuttering was removed. The column looked good. It was solid and, as planned, passed straight up through the building without actually touching either floor. By September 1977, Jack Beaumont had started rendering the outer surface of the circular wall. The following Sunday this was finished, but owing to a waning enthusiasm, further assistance from this direction was not forthcoming, and I subsequently took it upon myself to continue with the rendering, eventually completing the whole of the building. December 1977. The dome was ready to be placed on the circular wall. Not many members turned up to help with this, owing to the poor weather, but Robert Bowman, Paul Harper, Philip Heppenstall and myself succeeded in hoisting the ring segments onto the roof and then into position around the top of the wall. These were transported to the observatory on Robert's small trailer. Once onto the wall, they were bolted together, the steel verticals added, and finally the second ring bolted to these. With all the main steel components correctly fixed in position, work began on welding them permanently together. For this we used a portable welding kit and generator. The framework for the rotating ball race was the next part to be erected and finally welded into place. One has to remember that we had no proper platform to work from, only a plank placed across the circular wall, supported on an oil drum in the centre, and this in turn supporting a small step ladder. It was all very precarious. Despite the lack of equipment, by the end of the Saturday the main framework was solidly fixed in place. Work couldn't begin on the dome assembly, however, until the circular wall had been rendered with colour mix, a waterproof cement product that had to be applied with a Tyrolean projector. As no one had any experience with this material or device, and no desire to do it either, I decided to do it myself. Working balanced on a small step ladder perched on the top of an oil drum wasn't easy. Apart from this, the main difficulty was making the stuff stick to the underlying cement render and getting an even texture. It was also physically hard work, repeatedly climbing down to refill the projector. After a few false starts and a bit of practice, I managed to Tyrolean all the circular wall. Kirklees had specified that the observatory building had to be stone coloured, not the green shade that we preferred. We found to our horror that the colour mix came out a pretty bright orange. Upon inquiry, the makers of the product assured us that it would tone down as it weathered. Weathering was more rapid, however, than we anticipated, as heavy overnight rain washed much of my first effort from the north side of the wall, and my expertise with the projector improved as I had to redo large sections. Work recommenced in January 1978, and with the circular wall finished, I started screwing the wooden dome supports into place. These had all been pre-marked and tunnelized. Over the next few weekends the dome gradually took shape, as Philip and myself fixed the pieces into their correct place. This is one of the 6 ball races supplied to the Society by M.H. Mear & Company, on which the dome was to rotate. They were bolted into position around the top of the wall in the recesses provided. A local haulage firm kindly agreed to deliver the dome sections to the site. The weather was very cold, being December, and also dull and very windy. Note the balaclava worn by Paul. Also in the photo are Mike Henderson, Philip Heppenstall and Robert Beaumont. The sections were taken from the lorry and set out in piles in order of assembly. Despite the awful cold wind, work went ahead assembling the skirt. Mike and Paul watched the progress. The most crucial section to position was the circular top of the dome, to which all the other sections would be bolted. and I fixed this accurately using the registration marks we had previously made for the purpose during the last disassembly back at John Naylor's. It wasn't that easy, as I was balancing on a step ladder perched on a plank placed across the top of the circular wall. I'm wearing a plastic bag since, as well as being cold, it had started to sleet. The next step was to fix the sections of the dome into their correct position. These sections had also been carefully marked to ensure that the bolt holes would line up. We hoisted them using ropes fixed through the bolt holes onto the only corner of the roof we could safely use, as the wind was so strong they could easily be blown away. On this side of the observatory the wind tended to hold them in place. Jack Beaumont had also arrived, and the extra pair of hands were very welcome. Again, using the step ladder on its precarious support, Philip added the joint sealing strip to a row of bolt holes around the centre section, lined up one hole and passed a bolt through. Meanwhile I was on the outside, perched on a long ladder, fitting the sealant strip into place on the vertical seam, and then levering the sections into position and lining up the holes with a length of bar, and then passing the bolts through to be tightened up on the inside by Philip. By mid-afternoon the dome was half complete, and we could work in the relative shelter of the sections already in place. Finally, everything had been put together. For Philip and myself, it was the fourth time we had gone through the process. The dome was finally in position, but it still had to be mounted on its ball races. Over the next several weeks, Philip and myself continued with the assembly, fixing the shutter and bolting all the smaller items into place. This is a fisheye view of the interior of the dome. Philip has opened the shutter and rolled it around to its parked position. This worked fine, but rotating the dome proved to be a problem, as due to its weight it required two people just to get it moving. Note the plank of death across the wall, the only way to reach the top of the dome. With the dome now in place, my next job was to start levelling off the land and laying flagstones around the observatory. These had been supplied by Kirklees Council and were particularly thick and heavy, as they were originally used on the local pavements, which were being replaced with tarmac. I gradually extended the paved area all the way around the building, digging out and levelling the ground as I went. I eventually levelled the land right out to the surrounding walls seen to the right of this photo. As Jack Beaumont had not carried on with the rendering after completing the circular wall, I took on the job of continuing with the remaining walls. I wasn't an expert, but someone had to do it. Although a lot of cement failed to make it onto the wall, my technique got better, and by the end of the first day I had managed to complete the length of wall near to the doorway. Over the next few weekends I completed the rendering, and Philip and myself then etch-painted the exterior of the aluminium skirt. It was now beginning to look more and more like a real observatory. The inside of the dome was given an undercoat, prior to the dark blue final painting. The paints were donated by Bat Oil Limited, who also provided ample supplies of oil and grease for the moving metal parts of the observatory. This is another view, this time during the final top coat application. You can imagine the precarious stance on the small step ladder balanced on the plank of death seen earlier. With the interior finally painted, we could now start on the outside of the dome. The paint chosen was a two-part epoxy paint that needed carefully mixing in the correct proportions to work. It was by no means easy to reach the apex of the dome with the long ladder, which was all we had, and once there the paint, which at the start was quite liquid, readily blew off the brush with the light breeze, generally in the painter's direction. It was not long before we were both liberally coated. Over 2 weekends, Philip and myself worked our way around the dome. The paint gave a hard, shiny finish, both to the dome and also our jackets. Despite the difficulties, the dome was finished by the middle of the second week. With this important part of the work completed, I was free to use my newly developed expertise with a Tyrolean applicator to apply the orange-coloured cement product to the side walls of the observatory. It took a weekend to go around the building, but the result this time was much more even. Again, it was a matter of having to bring all the water to the site in plastic containers. I found it fairly easy now to go over the sections that were thinner without leaving much trace in the texture. Fortunately, the weather remained fine and rain didn't stop play or spoil the finish. With the walls now all a good solid orange, the next step was to paint the old cement roof with bituminous paint to ensure it being waterproof. It was also thought necessary to run barbed wire around the roof to hinder any unauthorised access. The difficulty of rotating the dome was solved by Philip and his brother Frank, who jacked it up and fitted a flat steel plate to the top of the wall, and then reversed the ball races, attaching them to the underside of the lower dome ring, where they could run on the level steel plate. In this slide, Philip is fixing one of the ball races into place. Even with the ball races in their new position, the dome was still quite difficult to move. The solution was to bolt a heavy-duty chain around the inside of the lower dome ring. This was kindly donated by BSL Power Transmissions. This slide shows Frank carrying out this work. Also visible is one of the 6 side bearings that keep the dome central as it's rotated. Frank and Philip, both engineers, had also constructed the winding handle mechanism for rotating the dome by literally pulling it along the chain. The sprocket engaging the chain can be clearly seen in this slide. At the top can just be seen the lower end of one of the original handles for manually rotating the dome. The gear mechanism was fixed to the interior wall in one of the recesses originally left for the ball races, which were now fixed to the underside of the ring. It was a simple matter now of turning the handle in order to rotate the dome. Reference marks were later painted onto the ring and the wall to ensure the correct dome position when closing the shutter. This is the jack handle, which is used for raising and lowering the shutter. The complete shutter in its closed position. Martin has just removed the closing bolts for the lower section of the shutter, and they are hanging behind the jack plate. The shutter section is about to be removed and placed against the dome on the rail for storage. The wheels that run along the lower dome ring, once the shutter has been lowered with the jack, are also visible, as are the handles that pull down the upper part of the shutter, so that it clears the inside of the dome. Later on I adjusted the wires to their correct length, and cut slots in the handles to take the ends of the cables. The handles came incidentally from my old lawnmower. The last step in the actual construction was the creation of a telescope support block. This was cast directly onto the top of the concrete pillar. Recesses were left for the fixing bolts and the manual polar axis wheel. Such was the weight of the telescope that something substantial was required in the way of attachment to the support block, and 4 32mm rag bolts were fixed in position and then carefully grouted into place. These 4 bolts had to be set correctly to take one of the 2 telescope support plates, and the wooden jig ensured that the position as well as the angle of the bolts remained correct whilst the grout set. The observing floor was also now a bit safer, as the possibility of falling through the access hole in the dark had been considerably reduced by the addition of a door. By the end of 1979, the observatory building was almost finished, after 4 years' work with hardly a break. All that it now required was the telescope. The design of the telescope was the responsibility of Philip Heppenstall, who had spent many hours at the drawing board producing the detailed plans necessary for its construction. Many of the smaller items were assembled in Frank Heppenstall's workshop in Netherton. It was here that the components for the dome chain drive and the bearing plates were made. Frank's workshop was not large, but contained all the necessary machinery for the job. Many of the smaller precision gears for the telescope drive were specially made for the telescope by Reliance Gear Company Limited in Huddersfield, and they were brought here and assembled. During a visit to an observatory in Manchester, I had noted that the professional mounting there used 16-inch drive wheels manufactured by David Brown Gears Limited. This was the size Philip had specified for our telescope, and so I noted the jig numbers stamped on them. Philip approached the company to see if they could make similar ones for our project. Despite the lapse in time, they still had the jigs in store and agreed to make them for us. These are the rough cast gears with a central steel disc and a cast bronze outer ring. The other items are the clutches for each axis and the stainless steel rod from which will be turned the matching worm gears. This is one of the same worm and wheels after its preliminary machining. However, the teeth still need to be cut by David Brown Gears on both items. Once the worm teeth had been cut, Philip and Frank started the assembly of the support plates for the drives to each axis of the telescope. Philip is here examining the declination drive plate, which carries the small drive motor and the worm. The smaller precision gears are still to be added. Back in March 1976, Philip had approached the David Brown Tractor Corporation with his plans for the telescope. The company thought it would make an excellent project for their apprentice engineers, and offered to build a telescope mounting. After 2 years' work it was complete, as shown by the front page of the company's newsletter. Most of the welding was carried out at the Lee plant. This photo shows some of the apprentices who fabricated the parts with their instructors. The main tube is on the right, whilst the fork to support it is in the centre. The round object on the floor is the mirror cell. This is another picture from the 1978 newsletter, and shows the assembled telescope at the David Brown Tractor factory at Meltham. December 1978, and this is our first view of the completed instrument. On the left is Kevin Dooley, who worked with the apprentices at Meltham, and together with Philip Eppenstall oversaw the assembly. In order to allow the assembly to be correctly balanced, I had cast a concrete disc with the same size and weight as the actual mirror. This can be seen at the lower end of the tube. In this slide, Kevin and Philip are examining the right ascension wheel and the motor drive assembly for the polar axis. For rapid slewing the telescope, the polar axis was also fitted with a large hand wheel, and using this we found it rotated very easily despite its weight. The Huddersfield Common Good Trust had kindly donated sufficient funds for us to purchase the telescope drive unit. This allows the telescope to be controlled in both right ascension and declination at the simple press of a button. The unit gave a variable speed to both axes and could be regulated for both diurnal and lunar rates of movement. The crystal rate of the unit was displayed on the control box, which can be seen on the wooden block just in front of me. Having given the telescope and mounting its final check over, it was dismantled once more, and the smaller items loaded into Robert's trailer to be taken up to the observatory. It was a bitterly cold day with a heavy snowfall when we left David Brown's tractor factory. Once up at the entrance to the observatory, the trailer was unloaded. In this photo, Philip and Robert are bringing in the polar axis assembly. This was no mean weight, and it took all three of us to get it inside. Although we managed to unload the fork between us, it was too heavy to carry. Philip is trying to lift it with a rope, but without much success. In the event, it was left out in the snow until we could obtain some heavy lifting gear. We didn't think anyone would run off with it in the meantime. The following weekend, Philip, his brother Frank, myself and Robert, Chris Devoy and Mike Henderson arrived at the observatory with a block and tackle, by the aid of which the polar axis and the supporting telescope plates were hauled up through the hatch onto the observing floor. The observatory now looked a little more finished off, as I had spent the previous weekend painting the interior of the circular wall with a special brick paint. Of course, it had to be orange to match the outside. Even though all the metal parts of the mounting had been specially treated, the first task was to cover the back of the lower support plate with grease, as once bolted into place on the pillar head, this was not going to be moved, hopefully, for many years. This was a heavy plate carrying two 36mm stud bolts, designed for adjusting the polar angle of the assembled scope. It was held in place on the sloping pillar head by the 4 rag bolts and 3 retaining brackets. In this slide, Philip, Frank and Chris are placing this lower plate into position. This is a better view of the plate in position with its 2 massive adjusting bolts. Note the hole near the base of the plate. This is to take a third but single 36mm bolt that is part of the second support plate. Philip is removing the upper nuts, which have rounded heads, to ease the movement as the upper plate angle is adjusted. Before adding the top plate, however, I gave all the exposed metal a thick coat of hammerite paint, as it would be inaccessible once the second plate had been bolted on. The next step was to add the second support plate that would be carrying the polar axis and ultimately the whole telescope. Philip, Chris and myself are lifting this into place onto the 2 stud bolts. This second top plate is another item that had to be thoroughly greased. In the centre can be seen the pin onto which the polar axis assembly is going to be placed. The pin was simply a pivot point to allow the polar axis to be adjusted east-west. Heavy bolts would actually hold it in place once the adjustment had been made. The polar axis is now ready to be lifted onto the pin, which can be seen better in the centre of the greasy top plate. The polar axis is now in place and being bolted down to the top plate. Later, once the scope had been assembled, it would be adjusted to point precisely north at the correct angle by means of the adjusting bolts. A week or so before Christmas 1978, the remaining parts of the telescope were lifted into place by means of a large crane, courtesy of Peabody Homes. It managed, luckily, to get right up to the building. The fork was the first part to be lifted and was set up ready for attaching to the cable. This was adjusted so that the fork would hang at an angle roughly equal to the polar angle and make it much easier to attach it to the flange on the polar axis. In the meantime, Robert had made further trips down to Davy Brown Tractors, and the tube of the telescope was also ready for lifting when the time arrived. The fork was now easily raised and manoeuvred through the opened slot. Inside the dome, Robert and Paul were able to pull the inclined fork through the shutter opening without any problems. Lining it up, however, was a little more complicated, owing to a tendency for it to hang a little crooked, and despite rotating the flange around with the polar axis, we had some problems getting all the bolts correctly positioned. In this photograph, Philip is giving instructions to the crane operator as the heavy mob pull the fork around. The fork is now finally attached, and Mike holds it steady as the cables are removed. Now the tube along with the mirror cell could be attached. This had a combined weight of almost half a ton. The lifting cables were attached to a bar which passed through the tube slots, and it was ready to be lifted from the trailer. The crane gently raises the tube and prepares to swing it over to the slot. It's now ready to be lowered into the arms of the waiting fork. It was a moment to record, and most of the members with a camera took photos. The examiner photographer was also there and recorded the event for the local newspaper. The tube was eventually pulled through the slot, positioned on the fork and bolted into place. The suspension bar passing through the tube slots can be clearly seen. We used this method to avoid crushing the tube, which would have happened if we had used the exterior handles as the support points. Fortunately, before the crane left, I noticed that the tube had been mounted the wrong way around on the fork, and some time was spent rectifying this mistake. Before he finally left, I persuaded the crane driver to hoist me up as high as he would go, to take an aerial photo of the telescope within the dome. I thought about 100 feet. The full extent of the crane would be a good height, but he obviously didn't think I was being serious, as he only raised me about 20 feet or so, not really high enough for an effective photo. In February 1979, Mike Henderson and myself set about painting the telescope. The paint, protective primer, undercoat and topcoat were kindly donated by Battery Limited in Huddersfield. Mike climbed into the tube from the open end and after rubbing down started to apply the red primer. I worked from the opposite end of the tube. The hard part was trying not to miss any areas that were out of sight. After several hours hard work, we had the whole telescope rubbed down and primed. With the winter weather being quite bad, one thing we noticed was that although the dome didn't leak per se, rain and snow readily blew up quite forcibly between the outer circular wall and the skirt, despite a good overlap and a space of only an inch or so. This is the inside of the dome after the February snowstorm. The fine snow even covered the telescope itself. This defect was cured when a rubber strip was riveted around the base of the skirt, which prevented the wind from entering. The examiner also did several spreads for the Society, even though the telescope wasn't yet complete. In this one, Gain Lee takes photos through a non-existent eyepiece of a non-existent moon, but it made good publicity. With the telescope now protected by a good red primer, I spent the remaining weekends of February giving the instrument its undercoat and topcoat. In the interim, Robert had made and fitted a set of steps to access the observing floor. I can now brick these in and close off the downstairs area with a sliding door. This room was to be used to store members' telescopes and the batteries that powered the lights and the main telescope drive. In the interest of safety, I had also fitted a banister rail and filled in the back of the stairs. Clearing up outside was also a task that had to be completed. I removed all the accumulated soil from around the observatory and rebuilt the stone wall at the rear. The area was then reseeded with a gift of suitable grasses, courtesy of Armitage's Seeds Limited. Within the dome, final touches were also still being made. The floor was painted with cement paint, and the motor units and drive wheels were fitted with aluminium covers to keep out dust, which might otherwise have damaged the delicate gears. The 6-inch solar and photographic telescope and the 4-inch finder scope had been fitted to the tube, along with special beta light optical sights. All that was now required was the main mirror. In February 1979, the mirror had been sent off to Fullerscopes to be aluminized, and returned a few weeks later to the club with its reflecting coating. It was to be installed in the mirror cell of the telescope, which had a 9-point suspension system. This consisted of 3 triangular plates, each pivoting on an adjustment bolt. The 3 long threaded bars, visible here, are for lowering the mirror into the cell. This photo shows me with the mirror ready for lowering. Once the mirror had been correctly positioned on the 3 triangular support plates, Philip adjusted the side screws, which kept it centralized within the cell. The secondary elliptical flat mirror, shown here with its supporting spider, was the only major optical item not made at the club. This important part was purchased by money donated by W.D.S. Ware, Esquire. Looking through the gap between the tube and the mirror cell, we can see Philip making the final adjustments to the retaining plates that hold the main mirror in position. After 4 years of almost unbroken effort, the telescope's first light was made at 11:15 AM on the 24th of June 1979. and Philip has the privilege of taking the first look through the instrument. The subject was Castle Hill, and even though there was a lot of heat turbulence and we were just viewing through the lower part of the shutter space, the image was very good, and we could clearly make out the faces of people looking out over the countryside from the top of the tower. Later the scope was properly collimated using a star image, and the mounting correctly orientated on the celestial pole. Final touches were the provision of plastic covers to the tube to reduce air currents and keep out dust. Philip and Frank also designed and constructed an adjustable observing platform. Following our first observations, the tube was carefully rebalanced and some adjustments were carried out on the clutches to reduce as much as possible backlash in the drive. Here Philip is making observations of the moon. The controller can be seen in his hand. Despite its weight, the telescope turned easily and there was little drift in the image. As well as observing favourite deep sky objects and the planets, many of our first observations were occultation timings, and I have a stopwatch dangling around my neck for this task. This is not ideal, as it needed an accurate reference timepiece. Later Martin built an electronic radio timer that picked up rugby time signals for this work. This gave a very precise timing for these events. In this photo you can see the adjustable observing platform and the covers to the declination drive. The eyepiece end of our 16-inch telescope, and just above it the specially made f4 4-inch finder scope. Hanging from this is the hand control set, whilst at the bottom near the base of the mounting can be seen Martin's radio controlled timer. The telescope performed well optically, giving fine detailed images of the planets whenever the seeing allowed. The large aperture also provided marvellous views of the Messier and other faint objects. It was used by club members both for personal observations and by school groups and the general public on special occasions. I took many photos using the attached 6-inch scope, but long exposures on deep sky objects with the main telescope was less successful. So this has been the story of how the observatory and its telescope were built. Its dome has now been in use for almost a quarter of a century and seems to be still going strong. However, there is another resident inside the white dome now. In 2003, the aging 16-inch was replaced by a new telescope, a 16-inch Meade LX200 instrument with GPS positioning and automatic go-to control, a fine modern telescope of much more manageable dimensions. But what happened to the previous occupant? Having retired to France some years ago, I learned that the old telescope was available, and so I approached my current club in France to see if they were interested in obtaining it, pointing out all the trials we had experienced in providing an observatory. In fact, I presented this slideshow. They were under no illusions about the difficulties that they might face. The response, as seen here in a clip from the local newspaper, was positive. And so, in a similar way to its entry back in 1978, the old lady was lifted from the dome for transport to its new home. This is the Huddersfield Examiner's colour photograph of the event. I arranged the transport, and the telescope duly arrived at its new home in Brittany. The story of the building of the new observatory cannot be dealt with here, except to say that, like 25 years before, all the components, mostly old friends to me, were cleaned, treated and repainted, rusted parts renewed or replaced, and new motors purchased. The telescope was then carefully reassembled, like so many years before. Its new home, with its roll-off roof, is not perhaps as imposing as the original dome in the UK. But the scope itself, in its new livery of blue and white, is a fitting tribute to all the members of HAPS who participated in its creation.